Hello. In this video, we introduce 8 basic graphs of functions which you will need to memorize. And then we take piece by piece and put them together and make all kinds of new functions. Let's get started. So to begin, I want to introduce these 8 graphs to you. Now, I'm not making them up. I'm actually showing you the graph that would happen if you were to actually input certain x values into an equation and find out what the output for y would be. The first type of graph you see on the picture is f of x equals a number. In other words, y, f of x, equals some constant. For example, if this was at the y value of, let's say, 2, we would say this is the graph of y equals 2. Now, the reason it's y equals a number is because y is constantly that number. You might have seen that before in other classes. But what's interesting about the graphs of y equals a number is we get a horizontal line, right? The slope is consistently 0, right? The slope is consistently 0. The y-intercept is at 2, but every single y value is at 2. So to get some easy points, you could say at -1, I'm at that location of y, in this case 2, and at +1, I'm at the location of y, which in this case is 2, as well as at the y-intercept, we're at 0, 2. For domain, every single x value is allowed to be hit, so -infinity to infinity. And for range, can you think of what the range would be? Yeah, the only y value that you're allowed to reach is the number itself. So in this case, just the number 2 in our example there. Now the second type of function that you should be familiar with already is the parabola. F of x equals x squared. Y equals x squared. Now if it's y squared instead of x squared, then we have a different type of parabola that would not be a function because it would be a parabola on its side. But since it's x squared, notice what happens. For x equals 0, when you square it, you're still at 0, so the vertex is at the origin. But when x equals 1 and you square it, what do you get? That's right, just 1. So you have the point 1, 1. But what about when x is -1? When x is -1 and you square that in parentheses, you get +1 again. So you get the point -1, +1. Now for each of these curves that we're going to show you, it's important that you memorize at least 3 key points so that when you see an x squared graph or a different graph that we're going to study, you can immediately put those points on the graph and remember what the shape is. So -1, 1, 0, 0, and 1, 1 would be my 3 key points for a parabola. Y equals x squared. Domain, any x value, right? Because you can square a negative or a positive x value. So domain is still -infinity to infinity, and the range actually does have a cutoff, doesn't it? Your range starts at 0 for y and goes all the way up toward infinity. So we'd say bracket 0, infinity. Now things get a little more interesting when we go to our third graph, f of x equals the square root of x. In this situation, what we're really dealing with is half of a parabola on its side, right? This is that case where we really had x equals y squared, but then we took the square root and only looked at the positive side. So what happens in this situation? Well, if it's a square root, there are certain restrictions on the domain, and we'll talk more about that in future videos. But in this situation, we would notice that because we have a square root, the values underneath it cannot be negative. So we'd start with our first input, potentially, of 0. And the square root of 0 is just 0. So the point 0, 0 would be one of our ordered pairs to remember for this graph. What's another easy x value we could input? How about 1? Well, the square root of 1 is just, that's right, 1. So another easy point is at 1, 1. So we had 0, 0, and we have 1, 1. Is there another easy point that we could put in for x to spit out our y? Well, yeah, you might be thinking, how about 2? Well, the only issue with that, while it is a point, you would get the output of the square root of 2, which is irrational, which is about 1.4 something. So I would recommend you put in an input which is a perfect square, like 4. So 1, 2, 3, 4 would be out here somewhere. When we input 4 into this function, we square root it and we get 2. So this would be at the y location of 2. So when x is 4, y is 2. So we're noticing that this is really a parabola on its side, but only the positive outputs. If we wanted the negative inputs, the graph would have been negative square root of x, right? That would have been a different graph. And we'll talk more about transforming graphs in a future video. The fourth graph that I want to point out to you is called the absolute value graph, and it's V-shaped. Let's talk about why that is. Well, we could input positive or negative values because absolute value allows you to do that. If you input 0, the absolute value of 0 is still 0, so we have a point at the origin. If you input 1, the absolute value is still a 1, so we have a point at 1, 1. So far, this is looking very similar to the points we got for the parabola, right? Similarly, if we put in a -1, its absolute value is still +1. So we're getting the same three key points, if you will, for the absolute value function as we did for the parabola. But keep in mind the shape is different. With the parabola, once you get to your next integer, like 2 or -2, you're going to jump up to an output of 4 because 2 squared and -2 squared, they're both 4. That's what causes that graph to curve up. But with the absolute value, if you input the next integer of 2 or -2, you're still getting an output of 2, which is why this is very linear. You basically have two linear pieces coming together, right? So with absolute value, you start off with the same three key points as you do with y equals x squared. But then things change rapidly after those 3 points, right? We either get a curve for a parabola or a v for an absolute value. Domain and range are exactly the same as for the parabola, so feel free to check that out. You can see why that is. Let's look at the next one, y equals x to the third power. Now this one is called our snake. It's really a cubic function. Parabolas are quadratic, and the snake is a cubic function because it's raised to the third power. So when I'm looking at this x cubed graph, what I notice is that I could have both positive and negative x values, so there are no restrictions on my domain. It's still negative infinity to infinity. But when I input 0, 0 cubed is 0. When I input 1, 1 cubed is still 1 times 1 times 1, it's 1. So I had the point 1, 1. So still it looks kind of like the parabola and like the absolute value graph. However, look at what happens when you input negative x values, like a -1. -1 in parentheses to the third power turns out to be a negative number, in this case -1. So we really get the ordered pair. -1 for input gives you an output of -1. So that graph is actually folding over what we call the origin. It has origin symmetry here. We may have mentioned that in the past when we discussed symmetry. Notice what the next points would be, the outputs would be, if you input the integers 2 and -2. 2 to the third power would have been 8, which is why this is jumping up here somewhere. And -2 in parentheses raised to the third power would be -8, which would be down here somewhere. And that's why your graph is rapidly stretched out there. It's rapidly increasing or decreasing depending on which direction we go. So for the graph of x cubed, you need to remember it's a snake with origin symmetry, and my three key points are -1, -1, 0, 0, and 1, 1. Another one that has origin symmetry is f of x equals the cube root of x. Now it's not as popular as x cubed, but it still is an important graph to recognize. So I notice here again, because it's a cube root, not a square root, I am allowed to input negative inputs there, negative x values, under that radical, because we can take, for example, the cube root of -8 and get an answer, a real number. The number would be -2, because -2 times -2 times -2 does in fact produce -8. So for example here, inputting 0, you get the cube root of 0, which is 0. Inputting 1, you get the cube root of 1, which is still 1, so we still have the point 1, 1. But inputting -1, now we get the cube root of -1, which is in fact -1. So we're getting this point at -1, -1. Now notice those are the same three key points that we got for x cubed, but the graph is growing differently. Before it was vertically stretched out, and now it's more horizontally stretched out. So that's a little bit different. The growth is different. We also notice why this is happening, right? Because if I were to pick a perfect cube like 8, way out yonder at +8, the cube root of 8 is 2, and that's why we're not growing with our y values as fast. So that would be the point 8, 2. And if I went out way out yonder to a -8, what do you suppose that the output would be if you input -8 into the cube root of x? Yeah, the cube root of -8 is -2, so that would be this point down here at -2. And that's why that snake looks a little bit different. So we have snakes that are vertically inclined for x cubed and snakes which are horizontally inclined for the cube root of x. But they have the same three key points that you'll need to memorize or at least be able to recreate quickly before we start moving these graphs around in our next video. The last type of graph, I said there would be 8, but I guess this slide only has 7 of them, so we'll skip one for today. The last type of graph is f of x equals 1 over x. Now this is called our reciprocal function. Reciprocal function, but it's just a special application of rational functions, which we'll be studying more in the future. Why it's called reciprocal is if your input is, let's say, 2, your output is 1 over 2. Those are reciprocals, right? So this is your reciprocal function. Now take a look at what's happening for this function. In the previous two graphs, domain and range were any real number, right? We hit every x and every y eventually. But for this graph, there is one restriction that we really need to pay attention to. And that is involving our denominator, right? Denominators can never equal what number? 0. That's right. You can't divide by 0, which is why the graph breaks apart at x equals 0. We're going to have a name for that coming up in our future video series on rational functions, where this is called a vertical asymptote. It's a line where it is a line that doesn't exist. It's basically a point in the graph that can never actually be reached. And that is because it comes from places where your denominator is always going to be 0 at that place, and that can't happen. So what ends up happening is your graph starts approaching it from each direction, doesn't it? How does that work? Well, let's pick some easy numbers for inputs. How about x is 1? If x were 1, then the function would say, take the reciprocal, 1 over 1, which is just, in this case, also 1. So 1, 1 is an easy point to get. And similarly, if x was negative 1, 1 over a negative 1 is a negative 1. And so that's why we get the point negative 1 comma negative 1. So far, this is kind of looking familiar, like the two previous graphs that had origin symmetry. But notice what happens now if you chose an input, let's say, of 2. If you take 2, what would the output be for this reciprocal function? Yeah, 1 over 2. That's why this graph is shrinking. It's getting lower. Its y values are getting lower as your x values are getting bigger, right? This is an inverse relationship. Like we studied variation in the past, this is inverse variation. So we notice that in this case, we'd have 2 comma 1/2 as an easy point. Now, because there's nice origin symmetry, you also would know that at negative 2, you're at negative half, right? Because we're saying when you switch the sign of your x, you get the opposite y. That's origin symmetry. But there's another thing that's going on. What if you picked a point like 1/2? That one might cause your head to spin a little bit. But if you said f of 1/2, what would that be in this situation? Yeah, 1 over 1/2. But that really means 1 divided by 1/2, which is really the reciprocal, isn't it? This is really 1 times 2 over 1. Multiplying by the reciprocal, or keep, change, flip if you were in Florida. That's how they usually teach you guys. So the answer here would be a 2. When x is 1/2, its reciprocal is 2, right? So that is what's happening here. When x is 1/2, we're jumping up here to 2. At 1/2, we jump up to 2. And so, again, this is an inverse relationship. As your x values get smaller, your y values get bigger. As your x values get bigger, your y values get smaller. That's what a reciprocal or an inverse relationship does. Notice in our domain and range, it looks kind of scary or intimidating, but nothing is new here. There's only one value for x and for y that we never reach, and that value is 0. Why is it true that we never reach it for y? Well, that's the idea of another asymptote we'll be studying later on in the semester, called a horizontal asymptote. And it's the idea there's a number that we're approaching but never actually reaching in this case. And that number, as we go to the right forever and as we go to the left forever, that number is 0. And that's why we have the same restrictions on our domain and our range. 0 cannot be included, so any other number is allowed. Negative infinity to 0, union 0 to infinity. Notice at 0, we've used parentheses, meaning we don't actually reach it. Okay, so this slide had a lot of writing on it. Feel free to back it up and try to recreate these points yourself. I would recommend flashcards to learn these basic graphs of functions, recognizing the name, the equation, the shape, and the key points before you move on to our future problems. Okay, let's go to our next slide rather. In this slide, we're going to introduce something called a piecewise function. So a piecewise function is just a function that is built using various pieces of other functions. When I used to teach AP Calculus overseas in Africa, I had my students at the end of the semester actually create their own roller coaster using piecewise functions. So they had to put different pieces of graphs together, combine them in a way that made sense, that was still safe for the roller coaster, and mathematically making sense as well. And then they'd have their function for any point on the trajectory of that path. Similarly here, we're going to look at some functions today which may be continuous or discontinuous. Notice for a roller coaster, it better be continuous, otherwise you'd fall off the track. Right? But in this case, we're going to look at a graph right now on the left side of the screen above me, where we have some options. Right? We see that f of x equals x minus 1. I'm looking at this one right here. X minus 1 whenever x is less than or equal to 1, or it equals x whenever x is greater than 1. So it's saying basically your output depends on your input, doesn't it? If your input is less than or equal to 1, follow this path. But if your input is greater than 1, follow this path. We deal with piecewise functions in real life all the time. If you ever do your taxes, you'll have to deal with piecewise functions, right? If you make between this much and this much, you pay this tax, etc. It's a piecewise function, okay? So taking a look at our example here, can we figure out which graph it could and couldn't be? Well, if I look carefully at the second and third graph, if I called this like A, B, C, and D, let's say. If I look at graphs B and C, I notice that those are graphs of lines which are consistently staying on the same trajectory, right? They're not changing. So I would personally rule out, if I didn't even know about piecewise functions, I would just say, B and C don't make a lot of sense for this, because that implies that they're the same trajectory no matter what your x value is. So you could immediately rule out B and C as the graphs that we're discussing here. Also, you could also notice what graphs those are if you're paying close attention, right? Graphs of lines you could write as y equals mx plus b, where m is your slope and b is your y-intercept. Well, here it appears, if I had given the points, it'd be easier to see, that as you go up 1, you're going right 1, which means that your rise over your run is really 1 over 1, which is 1x, so mx, plus b, and here my y-intercept appears to be the origin, so plus 0. In other words, this is the graph y equals x. Okay, so we know that's what this is really talking about. It's y equals x, that's the path. What is the graph to the right of it? What is graph C really representing? Well, it looks like its y-intercept is at -1. So this is really the graph y equals -1 for my b. But what's my slope? It looks pretty similar. Up 1, right 1, right? So this is still 1x minus 1, or just y equals x minus 1. Well, isn't that the two options, right? We were told that the graph is supposed to be x minus 1 for certain x values less than or equal to 1, and then x for certain x values bigger than 1. So looking at A and D now, we have two options, right? They both look pretty good as far as we can tell this piece here is the graph x minus 1, and this is the graph x. This is the graph x minus 1, and this is the graph x. But the difference is where we allow them to start and stop, right? In A, it looks like we're allowed to continue until we get to x equals 1. And in D, we're also allowed to continue until we get to x equals 1. But the real question is the open circle or the closed circle now. How do we determine that? Well, an open circle means do not include this location on this trajectory. The closed circle means please do include this location. So for A, we would be saying we are including 1 for the trajectory of x minus 1. But we're not including 1 for the trajectory of x. Doesn't that make sense with what we have here? It says you can follow the trajectory of x minus 1 up until 1 and including 1. So that's why this is a closed circle. And then we can switch tracks and go to the graph of x, but only for x values above 1. That open circle means anything to the right of 1 is fair game, but the closed circle means we can include that location. Okay. Now, if they had both been included, that wouldn't make a lot of sense because you can't be in two places at once, right? We look at x almost like a time. At this point in time, where are we? We can't be in two places at once, and that's why that would not be a function if they were both closed circles. So the answer here would actually be our first graph. It would almost be D, except for the closed circle was in the wrong place. Okay. So in our note on the right side of the screen, it says piecewise functions must still pass the blank line test in order to be functions. Do you know what that word would be? That's right, the vertical line test. To be functions, at every input x, you get one output. That's why we couldn't have both of those circles closed at the same time above each other. Notice another example in the graph on the bottom right corner of your screen. In this graph, it looks like we have 3 pieces again, not just 2. One piece is the graph -3/2 x minus 1, whenever x is less than -2. So which piece would that be? It looks like this piece, right? But notice it's less than -2, so it's an open circle at that location. Now you might be wondering, how did they get that specific location? Well, they could have graphed the entire line and then erased the part that they didn't need. That's one option. Another option is they could have said, well, what would have happened at -2? And if you would have put -2 in here, -3/2 times -2, you'd say that the 2's cancel and you're left with 3. And 3 minus 1 is just 2. And that's where you would have been had you been allowed to include it. Then they say the next pathway is x plus 1 between -2 and +1. That would be this piece, wouldn't it? Between -2 and +1. But notice at the ends, we have the or equal to, so we're allowed to equal the numbers at x equals -2 and at x equals +1. Again, you could either draw the whole line and then erase the piece that you don't want, or you could simply put in -2 and 1 and see where you would have been to close those circles up. All right, the last piece says y equals 3. Well, what kind of graph was that when you have y equals a number? That's right, a horizontal line. So we're saying y is the horizontal line 3 anytime x values are bigger than 1. So here is 1, and that's where we start our y values at 3 to the right. Notice I used an open circle because it said strictly bigger than 1. Does this pass the vertical line test? Well, yeah, because at this x value of -2, we only have one location for our output down here, not up here. The open circle is not included. And similarly, at the x value of +1, we only have one output at this value here, but not at the one above it. That's an open circle, so it's not included. Okay, so the things that you'll be practicing in this set of problems that you'll be working on will be 1, working with those library of function graphs, and 2, interpreting them and reading the pieces carefully in order to draw pictures of piecewise functions. So let's take a look at our next slide and see how to put all this together. So in this slide, we've given you a real-life example. Like I mentioned, there's lots of real-life examples of piecewise functions. Here in this case, they tell us that a t-shirt company sells t-shirts for $12 a piece. And if you buy, that's only though if you buy 10 or less. Have you noticed that? The value bundles, right? If you buy more, then it's a cheaper rate. So we notice that our first equation could be for every one t-shirt X that you buy, it's going to cost you $12. So 12 times X, 12 times the number of t-shirts that you buy. But that's only going to happen if you buy up to 10 t-shirts, so between 0 and 10. Notice it doesn't include 0 because you wouldn't actually be paying anything if you didn't buy any t-shirts, right? So between 0 and 10. So looking at the graph, or if you were drawing a graph rather, you would have to draw that line only between the numbers 0 and 10. Now, for the next part of the problem, it says if you're willing to buy between 11 and 50 t-shirts, then they cut you a deal and sell them for you for $10 a piece. So it's going to be 10 times the number of t-shirts that you buy for all t-shirt orders between 11 and 50. And that's what we see here, if X is between 11 and 50. And finally, they cut you even a better deal if you're willing to buy more than 50. So notice when X is bigger than 50, now it's only $8 a piece. So 8 times X, the number of t-shirts. And now we have a piecewise function. You could show this in Desmos.com on your graphing calculator or by hand that you have 3 different pieces of lines depending where your X values are, okay? Let's see if you are understanding what we're doing so far as we look at the example on the right here. It says write a rule for the piecewise function that's been graphed below. Now we have 3 pieces here. One piece on the left side looks like a horizontal line at the y value of 4. So if I was starting off my function, I'd write f of x, and then I'd open up my braces. I'm going to need 3 pieces, so I'm going to have enough room for 3 lines. So take a moment to pause the video and see if you can do this on your own. Okay, so let's see how you did. When you put your braces here, you next ask yourself, what's the first rule that I see? Well, I see this region right here. Y is always the y value of 4 until I get to the x value of -2. So y is always the number 4 whenever, you can write if you want, or just a comma, whenever x is what? Less than or equal to -2. Is that what you said? Great job. Let me get another color here so you can track with me better. What's our second graph? This is the one that's a little more complicated for students. It looks like a line with a slant, right? So how do we figure out the graph of a line with a slant? We usually use y equals mx plus b. I'm just writing boxes to represent the input there. So for the slope, we could figure out the rise over the run, or we could actually use points and use a formula. But I can see that if I was going from this point to this point, I would need to go down 1 and right 1. But if you go down 1, if your slope is down 1 and then right 1, isn't that really a -1 over a +1? In other words, isn't your slope a -1? So you could say this is really -1x, or -x. I'm just going to write -x. What's your y-intercept here? Well, you can see it. It's at the origin, isn't it? So 0 is your y-intercept. So you could write -x plus 0 or just -x. Now, when is that trajectory allowed to exist? That trajectory seems to be happening between the x value of -2 and the x value of +2. We have this trajectory. So between -2, x is trapped between -2 and x is trapped between +2. So notice I put -2 and +2 on the left and the right, and I put x in the middle. So now the question is, do I just use less than or equal to? Well, do we include or exclude those endpoints? At -2, it's an open circle. So for open circles, that means we're not including it, so we would have just said less than. So x is greater than -2, or -2 is less than x, either way. Okay, for the other endpoint, it's also an open circle, so we'd also just say the less than sign. So this is saying we follow the trajectory of -x for our output whenever x is between the values of -2 and +2 as inputs. Finally, there's one more trajectory. This one's a little bit easier. Let's see how you did. It looks like a horizontal line at the y location of -3. So it's -3. starting at the x value of 2 with a closed circle. So if you're saying 2 or more, that would mean when x is greater than or equal to 2. Is this the piecewise function that you had? I hope so. All right, if not, go ahead and pause the video and replay it and see if you can figure out where you went wrong, okay? Let's go to our next example if you're ready. It says write the equation of the piecewise function graph below and then write the domain and the range. Here again we have 3 pieces that we're going to have to recognize the type of trajectory each of them are and then when they're allowed to occur. Okay, so again, feel free to look back in the video in your notes and come back to me when you are ready to see how you did. All right, let's see how we did. So we begin to write a piecewise function by writing the name of our function, in this case f of x. It could have been any function, g of x, h of x. And then notice how many pieces we have. 3 pieces, so we need at least 3 lines for our function. The first piece may be a little bit unfamiliar to you, but I hope not. It looks like what kind of shape? That's right, it looks like a parabola that opens up until we get to the point of x equals 1. So the parabola has a vertex, I drew it badly here, but it has a vertex at the origin, 0. It hasn't been moved at all. Once we get into our next video, we'll notice that they can be moved, so we'll have to be able to recognize that and interpret that correctly. But right now, it's just the regular parabola, y equals x squared, until we get to what x value? X equals 1, right? So how do I write that? Well, just f of x is my y, so equals x squared, comma, or the word if. X is less than or equal to 1. So x is less than or equal to 1. Hopefully that's what you wrote. Let's look at our second piece. For the second piece, I have this horizontal part, and it looks like that horizontal part is the y value of 3. So that's like y equals 3, and it's between what x values? That's right, 1 and 2. So how would I write that in my piecewise function? Well, the y is already here. Y equals 3, comma. Whenever x is trapped between 1 and 2, we always put the smaller number on the left and the bigger number on the right. The question now is, do I include or exclude each endpoint? At 1, we have an open circle, so that would strictly be less than. So x is greater than 1 there, or 1 is less than x. But at 2, we have a closed circle, so that would be less than or equal to. So between 1 and 2, where we don't include 1, but we do include 2, the y value will be at 3. Okay, so notice here, if you had an input of 1, which trajectory would you be following? The first one, right, x squared, because that includes 1. But if you have an input bigger than 1 and up to 2 and including 2, then it would be an output of 3. Finally, the last piece of this piecewise function looks like a line. A slanted line, right? And that slanted line, remember lines can be written as y equals mx plus b, our slope-intercept form. Can we tell what the slope is here? Yeah, we're going up 1, right 1, up 1, right 1. So if your slope is up 1 and right 1, it's really a positive 1 over a positive 1, which is just 1. So this line is really y equals 1x, and then what is our y-intercept if we allowed ourselves to keep going? Well, we'd keep going, down 1, left 1, down 1, left 1. We would have landed here, wouldn't we? At 0. So this would have been 1x plus 0, or just 1x. So y equals 1x, between what x values? Well, starting at 2 with an open circle and going to the right forever. That arrow means go on forever. So that means we would say, starting at number 2, but only higher than 2, not equal to 2. So x must be greater than 2. So now, if someone were to tell you, I have an input, let's say, of 5, which of these 3 pieces would your trajectory be following? The third piece, right? And the answer then would be just that number 5. What if they said, I have an x value of 1.5? Which trajectory would they be following? The middle one, right? Because 1.5 is between 1 and 2. What if they said 2 exactly as your input? That's right, still the middle one, right? But if it gave you any number less than or equal to 1, you would take that number and you'd square it, and that's how you'd get your output. So that's the beauty of a piecewise function. It allows you to create a model for various different inputs, having different trajectories. Now, we would say that this model is definitely called a discontinuous model, right? It has big breaks or jump discontinuities in the graph. It would not be a good one for a roller coaster, let's say, because you'd want your graph to be continuous so you don't fall off the tracks. So as far as domain and range is concerned, since they asked for that, let's take a look at what we have here. Domain is the set of x values that are allowed to be reached. So if I look at my chart here, I include every x value less than or equal to 1. I include every x value between 1 and 2. And I include every x value to the right of 2. So have we excluded any x values? It might look like it on the graph with the open circles, but notice at the input of 1, we do have an output. And at the input of 2, we do have an output up here. So every single input has an output, meaning the domain is all real numbers, or negative infinity to infinity. How about the range? Is there any output that we never reach? Well, looking at the graph, we can analyze that. It does appear that there are some y values that would never get reached, and those are y values below 0, right? We notice that there's no numbers that are being output below 0. We also see a little gap in the graph here, so you might think, well, what about values between y equals 1 and y equals 2? Well, if that was the only part of the graph, then yes, you're right. There would be a part of the graph where the range has no values. However, notice that on the left side of this graph, we do have y outputs between 1 and 2. So we do actually reach those y values somewhere on the graph. And similarly, on the left, we're allowed to go up forever. So we can go toward positive infinity for our y values. So we would say for our range, any y value starting at 0 going toward infinity. So anything above 0 and including 0 will eventually get reached as an output. Okay, so we're going to do one more example, and then it's up to you to practice. Let's take a look. In example 2, it asks you to find the intercepts, but also to sketch the graph of this piecewise function. So can you interpret what it's saying and draw the graph? Let's take a look. It says f of x should equal x to the third power for any x values which are less than 0. So first of all, this would be you having to recognize what type of trajectory or path that is. What is the graph represented by x cubed? Y equals x cubed. Feel free to go back to your notes or earlier in the video if you forgot. Do you remember? Yeah, that was our snake that's vertically inclined, right? That was this snake where you had 3 key points. And what were our 3 key points for this snake? That's right, -1. What output does that spit out if you cube a -1? -1, good job. So that's like this location. How about 0? If you input 0, what does that spit out for its output? 0 cubed is 0. Good job. So that's the origin. And then what about the input 1? If you cube 1, you get 1, don't you? So that's this output. So we have our 3 key points. And again, in our next video, we'll be moving this graph up, down, left, right, stretching, shrinking, flipping, all kinds of fun. But for now, they haven't done any of that. They just say x cubed. No changes. So that's the trajectory, but only for what values? Yeah, that's right. X values which are less than 0. So what part of the graph would I have to erase, if you will? X values starting at 0 and higher. So I'd actually have to go to my graph and erase now. Oops, that was way more than I wanted to erase. I'd have to go to my graph and erase all x values which are starting at 0 and to the right of 0. In other words, this graph is the snake graph like that, but stops at 0, doesn't it? So it is the snake graph, but it stops at 0. So on the graph below here, if I wanted some points, I would include 0, but I would make it an open circle. So at 0, we're saying that's where there's a change happening. At -1, we're still at -1. If you wanted to get another point, you could use -2. Cube it, you'll get -8. So 1, 2, 3, 4, 5, 6, 7, 8. So this is at that point, -2, -8. And it's this snake trajectory. Okay, it's not going straight down, but it's curving slightly and slightly more to the left as we get more and more outputs to the left. What about our second piece of the graph? Y equals the square root of x for any x value greater than 0. Interesting. So what is y equals the square root of x? You can go back to your notes or the earlier video if you want. Yep, that was our parabola on its side, but only half of it, right? So at 0, for example, we had 0, so that was the point 0, 0. At 1, we said the square root of 1 is 1, so that was the point at 1, comma 1. At 2, we got a square root of 2, which is irrational, so we preferred perfect squares like 4 or 16 or 9, right? So if I input 4, the square root of 4 is 2. So I ended up at this location. So 4, comma 2. So those were my 3 key points for this graph, and it looked like a parabola on its side, but only the top half, only the positive half. Now, we're only allowed to draw that here, though, for x values which are bigger than 0. So if you're only allowed to draw it for x values bigger than 0, there's only one change we need to make. Do you know what that change is? Yep, at 0 itself, this should be an open circle because we're not including that point 0. So we would still say on our graph now, if we want to put it all together, at 0, 0, we have our open circle, just like we did for the previous trajectory. But now we have a point at 1, 1, excuse me, and a point, excuse me again, at 4, 2. So 1, 2, 3, 4, and 2. And this graph would look something like this. So the trajectory almost looks like it's the same path, doesn't it? This would almost be an example that, like my students made in Africa of something that they're building for maybe a pathway, like a roller coaster. But the difference would be we would have had to close up that circle because now we're saying you go until that point and you stop, and then you start over after that point. So that's still a gap in the graph. It's still discontinuous. There's a discontinuity at that location. Okay, so now we've shown you an example where you've had to graph it yourself when you're given the function as a piecewise equation like this. We've also had you recreate the piecewise function by simply looking at the graph. So this will take some practice, but the main thing you want to focus on before you even try piecewise functions is whether or not you know your basic library of functions, those 7 graphs we talked about. All right, so practice hard because math is not a spectator sport, and I'll see you next time.